Yeah, hello. In the first lecture, we talked about the concept of probability, where as a model for uncertainty, and we talked about the definition of probability and equally likely events. So we give a summary of all this material. Now we're going to talk about laws of probability. So that's what we're going to start with today. So I'm going to define now conditional probability. And by definition, the conditional probability of an event A given event B has occurred is given by this notation. P of A, that's the vertical line given B. Then by definition, the probability of A given B is this. Probability of A given B equal the probability of the intersection of A and B over the probability of B. Of course, provided probability here in the denominator is greater than 0. That's what this says. And the same thing if you reverse them, P of B given A. Let's focus on this. So what does that mean? So here is, let me give you an example from real life. So you woke up in the morning and you look out of the window and it looks really sunny. So you take your breakfast, you have shower, you break breakfast, and an hour later you're ready to leave the house for work. You check out your window again, or you're about to leave, and you notice it's getting really cloudy. So you go back and you pick up your umbrella and go to work. So what happened here from probability point of view? So that's your event A is you estimated when you woke up and looked out of the window, you estimated that the probability of rain is very low or nil because it looked sunny. And so you decided there's no umbrella needed that day. Well, an hour later, there was some new information came to light. That's event B. And it turned cloudy. So given the weather turned cloudy, what's the probability of rain now? An hour later, and that's when you revised your estimate of probability and decided it's very high, and you decided to take your umbrella. Okay, so that's the notion of probability. And conditional probabilities are very important. They appear everywhere because no matter what your probability that something will happen, it may change over time because other things come into play. So something to keep in mind. Now we but having new information does not always result in revising your estimate of probability. Sometimes the new event does not affect the probability you originally had, and in that case we call those events independent. New information has no influence on the probability. So two events A and B are said to be independent if given B, the probability of A still the same as it was before, P of A, no change. And if the two events are not independent, we say they are dependent. Okay. Now we can easily show that, and I will show you that in a minute. If the probability of A and B, if events A and B are independent, then P of A intersection B would be P of A equal P of B. This is useful, and if you are asked to verify two events are independent, because one way is to compute the probability of A, compute the probability of A given B, and check whether they are equal. Or you can compute the probability of A, probability of B, probability of the intersection, and check if this relationship holds. So where does this relation come from? It comes on from this. Let me go to my tablet. So if you remember, by definition, the probability of A given B is equal to the probability of A intersection B over the probability of B. But we said the two events are independent. That means this one here, P of A given B, is going to be the same as P of A. So if this is P of A, then I can replace that here and I will have P of A. So I have P of A equal P of A. Sometimes we can remove the intersection sign, P of A over B over P of B, and you can tell from here that probability of A intersection B is probability of A equal probability of B. That's what we have here. So that's where this comes from. And of course, if A and B are if A is independent of B, then B is independent of A. So so that means P of B given A would be P of B. Probability laws. The first one is called the complementation rule, which means probability of A is 1 minus the probability of A complement. And again, I want to show you that graphically. So if I have here a sample space, so this is my sample space S, and say this is here my event A, this would be my event A complement, and we know the probability of S is 1, so P of A, this P of A here, plus P of A complement would be the probability of the whole sample space, which is 1, and that's where that comes from there. Okay. The second rule is the additive rule, and so if you look at this one, the probability of A union B equal probability of A plus probability of B minus the probability of A intersection B. And if A and B are mutually exclusive, that means there's nothing in there, so the probability of nothing is 0, so that piece disappears, and the additive law would be this, but that's only a special case. You have to be careful with it. And I want to show you where this law comes from graphically. So let me go and get a new one here. Yeah, do you want to no? Okay, so I'm going to start here. So this is my sample space S, and this is my event A, and this is my event B. So I want the probability of A union B, which means I want the probability of this whole thing, A union B. So that's P of A. And let me mark this with these probability of A here, plus probability of B, and I'm going to mark this the other direction. And the question is, what do you notice happened here? Think about it, give you a second. Okay, so if you guessed it that this area is counted twice, you're right. Since we counted this twice, we have to remove one of them, so that's why we subtract probability of A intersection B. Okay, and if there's no intersection, that would be 0, and we'll get that special case of our law. So that's where this additive law comes from, or the law of addition. The multiplicative rule, let's talk about the multiplicative rule here. That's it's a rewriting of the definition of conditional probability. It's the probability of A intersection B equal the probability of A given B times P of B. And if you noticed, you take this part here, divide both sides by probability of B, that's exactly the definition of conditional probability. Because it's more interesting when you go to 3 events, because the probability is an extension of this, because now I can write the probability of A intersection B intersection C as P of A given B intersection C times P of B given C times P of C. Or you can do it starting with A and then condition in that the other direction. So I say P of A times P of B given A times P of C given B intersection C. And if the events are independent, then P of A intersection B would be P of A times P of B. Same thing, if I have three events that are independent, then it's going to be P of A times P of B times P of C. That's the probability of their intersection. And basically that's it. So that's an exercise for you to compute probabilities of events, probability of their intersection, unions, conditional, check independence. So I'm going to let you do that. So maybe you want to pause the video at this point, go over this exercise, make sure you can do it based on the information we discussed, and continue. There's another law we can talk about, law of total probability. Actually, we want to get to Bayes' law because that's very important in probability. So here I have the probability of A equal the probability of A intersection B plus the probability of A intersection B complement. Let me go to my tablet, see if I can explain it better. I clear. Alright, so in here, so I have my sample space again. This is S, and I'm interested in this event A. So I want to compute the probability of A, and I want to do it with two events. I have event A, here I want event B, and this is event B complement. So what I'm going to do first is take A and write it as this piece here, which is A intersection B, and this piece here, which is A intersection B complement. And then the probability of this would be P of A. Oh, these two pieces are mutually exclusive, so it's the probability of A intersection B plus the probability of, yeah, with tablets, it's hard to write. Anyway, this one here. And then in the next step, I'm just using the multiplicative rule. So that's P of A given B times P of B. I just want to make sure I got in the right order. Yeah. Plus P of A given B complement times P of B complement. So what you have here is basically use the principle of divide to conquer. So you want to compute the probability of an event like this. It's complicated, you don't know what that is, but you know, but you have these two events, B and B complement, you know their probabilities, and you also know the probability of A given B, and you know the probability of A given B complement. You know these conditional probabilities. If that happens, then you can really compute P of A using this formula, which splitting that event into simpler pieces and compute those pieces together, add them up, and get the probability of event A. So that's what this law of total probability is. All right. Now this takes us to this very important Bayes rule, which is really started by a theorem by Bayes and evolved into a completely new discipline in decision analysis. So if I have events B and B complement, and A is an arbitrary event like the graph showed you, then the probability of B given A, now things will be reversed, is equal to this formula. So in this case, we are interested in event B, which we call the prior or B complement, prior probabilities. Then something happens, which is event A, and then we want to revise our estimates of probabilities of B. We call them probability of B given A, and these are called the posterior or revised probability. Let's look at this one here. P of B given A. This rule is very simple. P of B given A is, by definition, it's conditional probability of the intersection over the probability of A. Probability of A, let's look at the denominator. This is the law of total probability from up there. And this one here is the multiplicative rule. P of A intersection B is P of A given B times P of B. So this is a very simple relation, but has far-reaching consequences. I'll give you an example here, quick example. A lab blood test is 95% effective in detecting a certain disease when it is in fact present. However, the test also yields false positive results for 1% of healthy persons tested. That is, if a healthy person is tested, then with probability 0.01, that's the meaning of that sentence, the test result will imply he or she has the disease. If this disease is really rare, only 0.5%, 1/2 of the population actually have the disease. What is the probability that a person has the disease given the test result is positive? Let's simplify this problem by thinking of it in terms of events. So if D is the event that the tested person has the disease, and E the event that the test result is positive, then if we summarize the data, that's P of E given D, given that the tested person has the disease, the probability the test result is positive is 0.95. So that would tell you this test is pretty good. So if you have the disease, you will be identified 95% of the time. And also we have P of E given D complement, that's the false positives. If a healthy person is tested, that means given that the person does not have the disease, there will be 0.01%, very small percent that would show the disease. And P of D, probability that a person has the disease, is also very small, and the probability a person doesn't have the disease is very high. But if you think of it now, really, actually, is that what we really want to evaluate how good that test is? I'm going to suggest to you to think a little bit about this event, P of D given E. What does that mean? E means the test result is positive, so someone is tested, they are positive. And D, that they actually have the disease. So if someone tests positive, what's the probability they will have the disease? That's different from here. If someone has the disease, they test positive 95% of the time. But if the test is positive, what's the probability the person has the disease? If you look at this, P of D given E, basically, that's by definition what it is. We use Bayes' rule just with these events, and we substitute. We have all the pieces here. That's P of E. What's P of E? 0.95. P of E given D 0.95. P of D 0.005. And P of E given D is 0.95. That's the same part as this one here, and that's 0.005. And then P of E given D complement from here 0.01, and P of D complement is 0.95. So you do these calculations and you get 0.32. So 32% of the people who test positive actually have the disease. That's pretty not impressive as this would suggest. And I want to stop here for time being, and then give you another lecture on the remaining parts of this chapter. See you later.